Ladies and gentlemen, welcome. Welcome everyone to tonight's proceedings, both here in person at the Royal Society's Victoria's Ellery Theatre, but also to those on Zoom webinar, and there are also some, we're also live streaming on YouTube tonight. Before we begin, in the spirit of reconciliation, we acknowledge that all of us are located on the traditional lands of this state's first scientists, the many different First Nations people who belong to the diverse lands and waters of what we now call Victoria. We're coming to you from Naarm, the lands of the Wurundjeri Woiwurrung people, and I invite everyone here tonight on this Zoom, the people on Zoom, on the chat function, or in the comment section on YouTube to acknowledge the traditional custodians of your own local country and join me in paying respects to elders past and present, and likewise we extend that respect to any Indigenous Australians who are joining us in our meeting here tonight. This evening we present the annual A.W. Howitt Lecture in partnership with the Geological Society of Australia's Victorian Division, and we extend a very warm welcome then to our friends and colleagues from GSAV who are with us tonight. This lecture commemorates the work of Alfred William Howitt, an early member and a councillor, indeed, of the Royal Society of Victoria. Alfred Howitt was known for his very capable bushcraft and role in recovering the only survivor of the Society's ill-fated Burke and Wills expedition. He recovered John King and effectively got King back. He found him at Cooper Creek. Howitt was a polymath, driven by his fascination for Victoria's landscape and also local Indigenous peoples. He pioneered the use in Australia of thin section petrology, I remember what that was, and chemical analysis of rocks. His fundamental contribution was the discovery and exploration of the Upper Devonian series north of Bairnsdale. He also makes studies of the Lower Devonian volcanics in the East Gippsland and compiled some magnificent geological maps of the area. In botany, his 1889 work, The Eucalypts of Gippsland, became a standard authority, and he collected hundreds of varieties of ferns, grasses, acacias, and flowering plants. Howitt's greatest eminence came from his work in anthropology, recording the culture and languages of the people of southeastern Australia, particularly the Gunai-Kurnai of Gippsland, which dominated his work from 1872 until his death in 1908. Tonight marks the 20th anniversary of our partnership in presenting the Howitt Lecture, and I think it's fitting to note the passing earlier this year of the inaugural Howitt Lecturer back in 2004, and that was Professor John Tallant, a Fellow of the Royal Society of Victoria, who was an enormous figure in the earth sciences and made remarkable contributions to teaching, research, and most notably research integrity. John Tallant famously and most courageously exposed one of the most notorious academic frauds of the 20th century, the Himalayan hoax. And you can read more about the Society's reflections on John's lifetime if you happen to have, you may have already read, the May 24th, that's this year, edition of Science Victoria. You might be lucky enough to find a hard copy on the table downstairs as you go out, but it's certainly there and available on our website. So I'd encourage you to have a look at the lifetime of John Tallant. Enough of that. Tonight, we're delighted to welcome Dr. Gresley Wakelin-King for her presentation, Australian Desert Rivers, so cool, so dry, so dynamic. I'll tell you a little bit about Gresley before I hand over to her for a presentation. She attained her honours in science, in geology from the University of Queensland, then moved to Alice Springs, presumably, well, I don't know whether it's necessarily warmer, but certainly desert, to work as a regional mapper for the Northern Territory Geological Society in 1985, volunteer work at the local Environment Centre, then introduced her to applied rangeland science, an experience that influenced her career trajectory. As a mapping generalist, she dealt with everything from deep crustal metamorphics to regolith, but eventually found her way to an abiding interest in desert rivers, their processes and how they support drylands ecosystems. Her research tools are geomorphology, sedimentology, and spatial science. Gresley worked as a geological contractor and took her career breaks for a family during the 1990s. But then while continuing client and family work, she undertook a doctoral research in Dryland's fluvial geomorphology and was awarded a PhD from La Trobe University in 2007. Since then, Dr. Wakelin King has consulted to clients across the Australian arid zone, including the New South Wales, South Australian and Commonwealth public sector. Her favourite landscapes are the Lake Eyre Basin, the low-angle, I love this, the low-angle fluvial fans in Western New South Wales. You can explain what they are, and the Upper Darling River. So with that, please join me. Gresley, please come up and say a few words of introduction. We don't get many geomorphologists, and I'm delighted to have a geomorphologist. You come and stand on this side. Is it a dying art, or is it just something a bit special, or is it? Why are you a geomorphologist? It is.
It's absolutely fundamental discipline because we all interact with the land, and we need to know how the land works to do that effectively. But as I guess most of us present will know, universities in Australia for the last 30 years have suffered at the hands of various mad decisions, and the geosciences particularly. So it's not a dying discipline. It's an incredibly important discipline, but we definitely need more geomorphologists.
Just explain it, because it is, to me, it's that intersection between geology, which is perhaps the pure science, and sort of, well, they got to say that. We got a GSAV here, but it's that, so it's that interpretation. One of our former presidents, and his photographs in the hall downstairs, is Edward Sherburn Hills. And yes, I knew. That's a little, so I actually made a point that I had a copy of Physiography of Victoria in my first year in geology years ago, and I actually made a point of getting a first edition because it's such an important book, and it's that wonderful descriptive stuff that I think we lose sight of a bit, which I'm looking forward to hearing from you tonight. That's why I like fluvial fans in the western slopes of the Dividing Range. So look, I'm going to let you get on with it. We've got a good audience here tonight, and we have people online as well. So you go ahead. We'll have time for some questions and discussion when you're done. You're welcome.
Okay, just give me a second, make sure that I've got the laser doodad happening. Yes, technology. Okay. Very good. Okay, Australian dryland rivers, they're alive and kicking. I'm really passionate about them. Before I get started on all the things that I want to say, I'd like to acknowledge the Wurundjeri people on the land that I live and spend most of my time on, and also the First Nation people across Drylands Australia, the places where I have worked and the places where I hope to work in the future. I'm going to be doing some definitions and contexts of the things I'm going to be talking about. I'm going to be talking about transformations. I want to re-examine what we mean by some concepts of rivers and channels. And along the way, I'm going to be talking about real-world applications. And the reason why I want to do that is because, as I was just saying, landscape processes underpin everything that we do. So whether it's engineering practices and standards or land use planning or anything right down to the goals that we enshrine in legislation and the language that we use to write that legislation, all of that, if it's in any way involved in landscapes or catchments, we need to know about the landscape processes. The Australian drylands, or the rivers of the Australian drylands, are places that are rivers that are in moisture-limited locations. They are usually dry or not flowing. And when they do have a flow event, they're transient flow events. So the channel typically will go from dry to beginning to a big peak or several big flood peaks and then die away to nothing. So a transient flow event. But aside from that, drylands rivers can be incredibly diverse. So the catchments can be anything from tiny to huge. The gradient is usually very low gradient, but sometimes can be quite steep and sometimes can be backwards. And the sediment load can be anything from 0 to absolutely lots. So we have a great diversity of drylands rivers types here in Australia. I should mention that in this talk, I've jammed in as many possible nice landscape photos as I possibly can. So I hope, as well as giving you something interesting to think about, I'm going to give you a galloping tour over as many drylands river areas as I have available to me. First question I get asked when I say what I do is, dryland rivers, you know, do they even work? People would say, oh, ho, ho, that'll be a really short thesis then. And I'm like, no, that's the point, no. So they're dry. Do they even work? Maybe they're just, you know, like normal rivers, but completely inert, like freeze-dried hiking food. There's nothing to it unless you add water. Now, if dryland rivers are just static, normal rivers, then there's actually no need for any extra research here, because they don't, you know, they don't do anything different. The other thing that people often subconsciously assume about dryland rivers is that they're somehow not real rivers. So famously, Charles Sturt, when he got to Cooper Creek near Windora, even though Cooper Creek there has a pretty big primary channel, he looked at it and he said, there's water here, but it's not actually flowing. So I'm sorry, I can't call this a river. It's just a creek. So the implication is kind of that dryland rivers are not really proper rivers. We don't really value them. And obviously, I think that's a mistake. So yeah, dryland rivers work. They work all the time. Even when they're dry, they're working. But they work differently. Drylands rivers, drylands fluvial systems are very complex. So here we've got Cooper Creek at the place where Charles Sturt said that it wasn't really worth calling a river. This is one of the narrowest places that the Cooper floodplain gets, and it's about 6 kilometres across and has a whole plethora of fluvial landforms. Drylands fluvial systems are complex. They are also really valuable. This is the Finke floodout complex, where the Finke River comes down and floods out into the Simpson Desert. Now, everything that you see that's red on there is inorganic, either sediment like dune fields or rock like Gibber Plain or Silkrete. So the red stuff is inorganic. Everything that's black or grey is plant community. So even though in the Finke floodout complex, there is not much in the way of channels or big deep flows or anything like this, but buckets of water comes down here and supports terrestrial ecosystems way out in 2 directions into the Simpson Desert, as you can see there. So even when they're dry or not visibly flowing, and even though they're different, they are still valuable. Excuse me, I'm just recovering from COVID, so I'm going to cough a bit here. I swear I am not infectious. When I was invited to give this lecture, I looked up A.W. Howitt, whose biography we've just heard. And the thing that really struck me about his life was that he had this transformative journey. So as a young student in his early 20s, he was a student in England's green and pleasant land, came out to try his luck in the goldfields, did not make his fortune on the goldfields, but in the space of a very few years became a quite accomplished, skilled in living in the bush, to such an extent that he was chosen to be the leader of the rescue party for Burke and Wills. And then after that, as we've heard, he went on to a big career in public administration and a long career of actively collecting information as a field scientist. Now, this really kind of resonated with me because I felt like Australian landscapes have been transformational for me as well. When I first came to this country as a young immigrant, frankly, nothing made sense. Everything was really confusing and the landscapes just seemed quite weird to me until the first time that I saw Central Australia, and that seemed to give it a big context. Fast forward some years later, and I was forced by unemployment in Brisbane to go and take up a job in Central Australia. And I was distraught. I was leaving behind, you know, my mum, my best mate, my boyfriend, my whole life to move into the desert. I thought it was going to be dreadful. Cried like a baby at the airport. Halfway across the flight between Brisbane and Alice Springs goes over the Simpson Desert and then Cooper Creek, and I'm like, tears forgotten. I'm just looking out the window going, this is amazing. So I had a really amazing time in Central Australia doing regional mapping. And I spent a lot of time either walking along or camping in dry creek beds, and I started to get really curious about these landscapes. So when I had the opportunity to do my PhD, I decided I wanted to find out more about how drylands rivers work. Now, the third transformation here is the transformation of aridity. It's not that drylands rivers are dry. That's not what makes them special. It's that the state of being in dry country actually changes some of the things that are really important to how rivers work. This is a topic that I could talk on for hours, and I can't do that, so I'm just going to give you the high points here. Aridity gives you really variable input of water. So the timing and the location of rain is obviously highly variable and uncertain. Also, the intensity is very variable and uncertain. When the rain falls on a hill slope, it is not, as it is in the temperate zone, sucked into the soil and then gets into the river, mediated by the soil processes. It hits the ground and is shed by the ground surface. So it comes as surface runoff, Hortonian runoff. And that makes it really very vulnerable to rapid and transient surface flow events. And then finally, the hill slope that the rain is falling on also has a very varied characteristic of its runoff coefficient, and I'll be talking more about that in a minute. There's also variable throughput. So as a flow event travels down the river's drainage network, the volume of water carried by the river, after a certain point, the volume of water starts getting smaller and smaller and smaller as water is abstracted into the channel bed or the banks or taken up by the trees or whatever. So the throughput is variable, and then it's made even more variable because the patchy distribution of vegetation means that evapotranspiration is also kind of patchily distributed in the landscape. Finally, and this is another great big story, the nature of aridity changes the vegetation, landform, spatial relationships in a way that influences things like bioengineering, and that has implications for landform and landscape evolution, and there's a whole bunch of things happening there. So these are the reasons why aridity changes how rivers behave. Straight away, we come to our first practical application. Nationally, we have a cultural bias in our collective vision of how rivers operate. And this hinders a good understanding of how our drylands rivers work. Basically, dryland rivers share many of the fundamental structural kind of basic points as all rivers do, but there are enough areas of difference that if you try and manage the two things identically, you're going to be in for a world of hurt. And let's see an example of this in river condition assessments. So if you're an Australian public sector department, sometimes part of your job is to make an assessment of how good the condition is in a piece of country. You have to go out and you say, is this okay? You know, is it doing all right? Or are there damages or or problems here that we need to address with some kind of management solution. Condition assessments have usually been developed for wet rivers. All the ones that I've been able to find have their origin in wet rivers. And typically they have some kind of a scorecard approach. So you go to your field site and you're given a set of criteria by which to judge how good that site is. And for the things that have to do with habitat or supporting ecosystems, the scorecards will typically include things like aquatic biota, fish or macroinvertebrates, or water quality, things like salinity. Now, clearly, if you're a dry river, you've got no biota to speak of. We just don't do that. And there's no water to measure anything in. So if your scorecard is here, your river is going to get a pretty rubbish score, even if it's in really good condition. That's bad enough. But there's actually a much more pervasive problem, I think, here is that it introduces a huge sampling bias into how we monitor our rivers. So we tend to pick places to go and assess the health of our rivers where there are places that have got aquatic biota and water to look at. So we we're ignoring a really large proportion of our drylands rivers, either entire small river systems that don't have water holes or any bit of the larger river systems that happen to not have water holes, we kind of ignore. Obviously, that's a bad thing. Let's talk about the Australian context now. As a continent, we have very low relief. We're really flat. New Zealanders will tell us often and often. We have occasional bits that are steep, hills and ranges, but mostly very low gradient. We have subtle but significant neotectonism. So despite the fact that we don't have, super flashy, impressive earthquakes like our cousins in New Zealand, all across the continent, there are places where there has been folding or faulting or warping sufficiently recent that it still has an influence on the landscapes that we see today. And that means it influences things about our rivers. This is a really important one. We have deep regolith. So the regolith is everything that isn't either fresh air or fresh rock. The regolith includes any sediment like sand dunes or soils or whatever, includes things like weathering profiles. There's lots of different kinds of regolith, but one of the main points here is that some of the regolith has got really high runoff coefficients. So if you imagine rain falling on things like silkrete or Gibber Plain or these pale weathering profiles that you see here, the rain is just shed off that kind of regolith like anything. Whereas the photograph on the right, those are cracking clay soils from the Thomson River. Some of you may know that kind of soil as vertisol or black soil plains or Gilgai country. So this stuff is just like a ginormous sponge. It has to be really, really, really wet before it sheds any rain at all. Excuse me. Finally, because of where we are on the globe and because of our topography, we are a largely moisture-limited continent, but nonetheless, when a big weather event happens, it can sweep far enough inland so that we get big dumps of rain or big flows of water into the inland. So we get flows from the northwest, the north and northeast, and also up from the south. Now, all this context means that we are actually in some ways dissimilar to some of the other drylands that people know best. So the west of the United States and the Middle East are places where some of the foundational literature in geomorphology and dryland sedimentology has been written in these places. But you'll see I've put an X over them. That's because Australia is not very like those places. We are different. This means that ideas from other drylands don't necessarily apply here. And an example that I'm going to use here is braided rivers. So braided rivers is one of the well-known river types. There was some really important work done midway through last century that talked about the different conditions that promote braiding versus meandering, that kind of thing. So braiding in rivers is a thing that people get sometime in early high school physical geography and get it again and again through probably undergraduate landscape education. Braiding was once thought to be characteristic of desert rivers. So here's an example from Urumqi in China. And it was so characteristic of desert rivers that the Australian geomorphologist John Mabbutt, when he wrote his textbook on desert landforms, he talks a lot about braiding. The difficulty of that is that we don't actually have braided rivers in drylands Australia. The things that we have previously been describing as braided are multi-thread rivers, yes, and the threads of the river weave back and forth, so it looks like it's braiding. But the key point here is that braiding is about high energy flows and mobile bars and channels, whereas in Australia, what we have is low energy flows with stable bars and stable channels. So we have anastomosing multi-thread rivers, like this one in Arkaringa Creek, and you can see that is a picture of one of the threads of channels in the Neils, and you can see that it's really very stable. Nothing is moving there. Similarly, the other kind of multi-thread river that we see a lot of is anabranching. So here we are back at Cooper Creek near Windora. The main channels, the primary channels, are the ones where you can see they're outlined in black. That's the riparian vegetation along the channel banks. And in some places like there, you can see the glint of water. So anabranching is where the channels depart from each other and are hydraulically independent, but then they come back together again. So again, they're multi-thread, but again, they're low energy and stable. They're not braided. So there's a whole big discussion about braiding, anabranching, and anastomosing. I recommend the reference by Moron et al. 2017, where they go into a lot of detail about the different ways that these things come about, and then I've applied that to the context of the Lake Eyre Basin. Okay, Australian dryland rivers have so many special characters. I had to kind of list them to get them all out of my head, otherwise I was just going to waffle on here for hours. And I can't talk about all of them. I have to talk about one. This is like being asked to pick a favourite child. So I'm just going to talk about highly variable flow regimes and what that means for channels and flow paths. But there is all this other stuff as well, right? So, okay, I'm not going to start waffling about those, otherwise I won't stop. Let's have a look at some basics here. Channels and floodplains. The channel is usually described as the main pathway of water flow. It's a continuous and defined path. In fact, that is enshrined in Australian legislation in some places. And the channel is created by the active flow of the water. So the amount of water, the amount of sediment that it carries, the speed at which it travels, all these things combine to give the channel its characteristic width, depth, cross-section, plan form, way that it interacts with the landscape. And this means that we examine channels to work out how the river is behaving. So typically when you're measuring things in channels, you're measuring numeric things like flow volumes or depth or width or something like that. The floodplain is defined by the ISC as the low area that flanks the stream and gets flooded every couple of years. There is often a connotation of the floodplain being a flood basin or an area of overflow drainage where the water comes out and then goes back into the proper river again. Floodplains are where people live and work. So the things that we tend to measure on floodplains tend to be things like flood risk. This is a cross-section of a hypothetical a channel banks, and then the valley that the channel is sitting in with a little bitty bit of floodplain here and here. Okay, so when we're talking about flows, there are some words that we use to describe the kinds of flows that we get. So, for example, base flow in a temperate perennial river, base flow is the amount of flow that you would expect to see in the channel most of the time. Bankfall, when the river is absolutely up to the banks, but before it started overflowing onto the floodplain, that happens every couple of years, and that's considered to be what's called channel forming discharge. So it's like the amount of water that has the most ability to create its landscape, the most geomorphic activity. And then anything over that, obviously, that's a flood. The symbol that we use to describe discharge is Q. And when we talk about rivers, when we talk about flow events, we often talk about them in terms of the return interval of a flow event. So an ordinary flow, the base flow, that's something that you see all the time. So its return interval is like less than a year. A channel forming discharge, a lot of research has gone into working out how often a return interval you get for a channel forming discharge. A lot of figures are around 2 to 3 years. Obviously, it varies. And then the bigger floods we talk about tend to be things like the Q50 or the Q100, the 50-year flood or the 100-year flood. Now, there are reasons why we don't use that terminology much anymore, but for the sake of simplicity, we're going to stick to that tonight. But the thing about the Q50 and then the Q100 is that these are flows that are large enough that they're kind of irritating or destructive or in some way detrimental to the human experience. So if you have a bridge over a river, you might design it to accommodate the Q50 or the Q100. So I want you to see there the space that I've given between base flow, bankfall, and Q50 flood. This is a temperate perennial river, and this is what it looks like in a drylands non-perennial river. So base flow isn't a thing. It's not what we do. The ordinary flows, if you like, the Q1 to 5, say, could be anywhere up and down that channel, that banks, that valley margin, could be anywhere. But the key thing here is that the Q50 is a lot bigger. So let's just go backwards and forwards between that. That's your temperate perennial, that's your drylands. And so what we're talking about here is high variability and low variability flow regimes. As an example, here is the hydrograph of the Colorado River over a number of years before and after they installed the Glen Canyon Dam. So this is its natural flow pattern as a highly variable drylands river. Got lots of low flow, but the floods, when they come in, they're really big floods. And this is what happened to the river after they tamed it. Had more reliable base flow, but it didn't have big floods much at all. Okay, so this is the difference between highly variable and low variability river flow regimes. What that means in human terms is something like this. If we live near a low variability perennial river, we've got reliable in-channel water and we've got an accessible floodplain. Whereas if we live near a drylands river, we can expect to have a dry channel a whole lot of the time, but we can also expect widespread inundation. So there are some things then that we need to consider about channels and flows in highly variable rivers. On the top right there, that's the main channel of Cooper Creek. That's Menke Waterhole. And the bottom photo there is a secondary flow path in the Diamantina River. one might call that floodplain, but it's actually a flow path. So in highly variable rivers, obviously channels are a type of flow, and obviously they're important, but they are not the only type of flow, and they're not the only important flow. In fact, channel is not even always a meaningful concept here. And the in-channel flow is not what uniquely defines the river. Floodplain level flow exists. It is a thing. It is also important. And it is part of the flow path, that defines the river. Let's get this one out of the way quickly. I have had people say to me, flooding in a river is just a waste. We could be using that water. Flooding is not a waste, okay? Floodplain level flows are what drive the boom and bust ecosystems that are characteristic of the drylands. I've got to say, this is one of the more surreal experiences of my field life. This is a bunch of us getting together to watch the fish cross the road at the Algebuckina Causeway. So the Neils is having a nice old flood here, and the channels are flooded and the floodplain is flooded, and that's great, and the fish are migrating as you'd expect. But the thing that's happening here, it's not that the fish are migrating in the channels. They actually don't want to be in the channels. They get out of the channels and they migrate across the floodplain and go to a different flow path and go to a different channel in that river system. So the floodplain level flows are absolutely important in these ecosystems. They're also equally important for the terrestrial ecosystems. That's also the Neils. I've never had such a snaky field experience in my life. Look at all that grass. Anyway, so terrestrial ecosystems too. But the other thing that I think that people don't truly appreciate is that flooding is important also for the physical aspects of the landscape. So widespread inundation is important in recharging groundwater in those places where the river recharges the groundwater. And the flow energy, when you get a flood that's big enough to inundate and flow across the floodplains, that flow energy is strong enough to maintain and renew the physical habitat. So particularly the primary and secondary channels and the waterholes absolutely depend on high energy flows to maintain their depth. Okay, so let's see some of the places that makes me so sure that floodplain level flow exists. This is the Upper Darling River in New South Wales. That black outline is the Darling fluvial corridor. I was fortunate recently to be able to do some floodplain examination of the floodplain landforms in conjunction with the inundation footprints of two floods that took place during 2022. So neither of these floods were extreme in any way. The dark blue flood that happened early in 2022 was not a very big flood. It was like a recurrence interval, roughly 15 years. The larger flood, which you can see is occupying quite a lot of the floodplain in places, that was bigger. That was nearly a 50-year flood. But still, that's not very big. You know, we're not talking extreme events here. A 50-year flood is something that we expect to happen. And to cut straight to the answer here, the thing that I was finding from this combination of inundation footprint and examining the landforms is that the Darling River, the Darling fluvial corridor, is an integrated network of the main channel and minor channels and a whole lot of different kind of floodplain flow structures. So let's look a bit closer in and see what this looks like. This is the Darling River main channel at the township of Tilpa. In this Google Earth image, that black dot there is Tilpa Township, and obviously you can see the sinuous path of the Darling River. Everything that's red in that Google Earth image is dunes or in some other way is above the level of fluvial influence. Everything that's grey or tan coloured there is within the fluvial corridor and potentially within the reach of fluvial influence. This is a detrended digital elevation model overprinted with the 15-year ARI flood, so that's the smaller flood. And already you can see that although clearly there's flow occupying the main channel, there's also a whole heap of water occupying these networks. And these networks don't particularly interact with the main channel. Some of them go back into the main channel, but some of them take water off from the main channel and they shoot off somewhere else. And that circumstance is even stronger when you look at the 50 ARI flood, which occupied most of the flood path. Excuse me. So looking at this, what I was able to do was identify different flow paths. The yellow dashed line, that's roughly the trend of the Darling main channel, but these white lines are other flow network directions. And even this one here, which is parallel to the main channel, is still largely independent of it. So this situation where the high-level floodplain flow does not necessarily have to be in lockstep with the main channel is obviously well known from Cooper Creek and parts of the Channel Country. This has been the subject of University of Wollongong research team for a number of years, but here it is happening in the Darling as well. So what does this flow path, what do these flow paths look like? Here in near Wilcannia, so a little bit further downstream, there's the Darling main channel, and this is a flow path, and this is another flow path. And what we've got here is a number of floodplain swales and bars and some channel segments. So those are the elements of that flow path there. And then we've got quite a different looking situation here in the Neils. We've got alternating channel segments and very poorly defined diffuse flow. So here you can see one little bitty channel segment. Here you can see another one. But what the flow is doing, the flow, when the river is fully flooded, it occupies this entire area is flow path. And this is one major flow path that goes from diffuse to channelized and then back out to diffuse again. This brings us to another real-world application. If we are only monitoring what's going on in the channel, we are missing part of the story. So the examples I'm going to give here are about monitoring flow volumes, but this same concept applies equally to whether you're looking at sediments or biota or anything like that. If you're only looking at the channel, you're not seeing the whole picture. So this is Tilpa again with both the flow events plotted. This is the floodplain topography, obviously vertically exaggerated, and that red line across the top is the level of the larger of the two floods. This blue area is the discharge, the volume of water that was captured at the Tilpa gauging station, and you can see all these volumes of water that were not measured in the gauging station. So clearly we've missed a lot of information there. But the thing is, when you're measuring flood, when you're measuring the size of a flood by how high it rises in the channel, that's only good insofar as your flow is contained with the channel. Once your flood starts to go out instead of up, you've got to do something completely else. And this is a place where it might matter. So you all know what a culvert is, right? A culvert is the thing that allows runoff water to pass underneath a road or a railway trestle or whatever. Obviously, when you put in a culvert in a redeveloped road, you size it to match the expected volume of the water. And that's obviously an important thing. But what tends to happen in Drylands Australia is that the people who design these things go along and they say, aha, here's my little bitty creek, there's my little bitty channel, that's how big the culvert is going to be. So you get situations where the culvert is designed for the in-channel capacity. They are not designed for the capacity of the entire valley, and that is the amount of water that actually needs to pass through that culvert. So what happens then is you've got the culvert is too small. You get what's called flow concentration in the culvert. So the flow is concentrated, it speeds up. Its stream energy is greatly increased. You trigger erosion and you get gullies initiated. And the gullies, this is not just a little local bit of erosion. This is a gully network that's going to propagate upstream and downstream. Yeah, exactly, everywhere. So all across Australia, all across Drylands Australia now, we are doing damage to the countryside with culverts. Another application of understanding that floodplains carry flow and that floodplain level flow is a normal behaviour for dryland rivers is that we need to plan for it when we decide how we're going to be using that floodplain. So this is Fitzroy Crossing in WA, which you may remember had some really spectacular floods not long ago. This is a Google Earth image, and the squares are residential areas that were visible on the Google Earth image. That's the footprint of the flood. Now, I'm obviously not saying that people shouldn't live there. People should be able to live where they like. But if you're going to take a decision to live somewhere, you need to be able to plan for the conditions that you're going to experience when you're living in that place. To be able to do that, to plan for it, we need to acknowledge that this floodplain level flow exists and we need to be able to map it. So here is Narrandera, which is at the apex of a low-angled fluvial fan in New South Wales. So low-angled fluvial fans are kind of cool, right? Oh yes, I love having an audience that agrees with me about that. So you get a low-angle fluvial fan when you have a river coming out of a more or less constrained flow path and it enters into some broad plains like the Western Plains of New South Wales. And the fluvial fan develops by vertical floodplain accretion, that is by flooding, and by channel relocation. So basically, if you imagine my arm is the channel and it's coming out into the plains, it's going to flood and drop mud everywhere, and every now and then the channel's going to move somewhere else. Okay, that's your low-angle fluvial fan. Now, the downloadable digital data set, the topographic data, which is the basis that people use to make their decisions, has got the Murrumbidgee River nicely mapped. There's its channel. And here's the little distributary that goes off to the side. Narrandera's about here, right? So, you know, that's clear. We see where our flow paths are, except if you look at the geomorphology, those are the potentially available flow paths. Now, I'm going to be clear that the Narrandera Town Council and the engineers that they hired to do their flood mapping, they're absolutely across this, right? They've got all this stuff in their complex flood plans. But when you have to use language like overland flow that has all these connotations of unusual, unexpected, kind of weird behaviour for a river, and we really wish it didn't do that, it's really hard to get the stakeholders to come along on a journey of accepting that this is what we need to take care of. Okay, let's go back to our hypothetical channel and our very, very, very many different places that the Q1 to Q5 flood heights can reach, and the very many different places that the other floods can reach. The thing about a highly variable river is that the flow energy, the channel forming energy, is going to be highly variable in space and time. That's clear. So how is this expressed in the channel morphology of our drylands rivers? You get a whole lot of weird stuff. So here is macrochannels. A macrochannel is a compound channel. So you have smaller channels set within larger channels, and each is related to its particular flow size, and all are part of the current flow regime. And for the bigger, more complex system, like here in Cooper Creek, mapped by Knighton and Ensign, you can see that there are different inundation levels, different, if you like, concordant floodplains, I guess. So a macrochannel is a way that some of our dryland rivers behave, and one of the connotations here is that there isn't a single value for channel forming discharge. Discontinuous channels are absolutely a thing in drylands rivers. So even the really, really big channels like the Cooper Creek primary channel here, if you go only a fairly short distance upstream, the channel virtually ceases to exist. The intake area for that big waterhole, that waterhole is like 50 metres wide, it's about 30 or 40 metres deep, it's about 10 or 20 kilometres long. So it's a big deal, right? But this is the intake area. It's a tiny little minor creek and a whole lot of floodplain level flow. So that's an example on a really big scale. I have to say I've looked up and down the Diamantina River. I haven't found a single continuous channel in the whole Diamantina River that I could see on Google Earth anyway. This is absolutely one of my favourite examples. So this is the Neil River. This thing hasn't got a continuous channel to save its life, right? This is the width of the entire river valley. It's also the width of the entire flow path. When this river is flowing, this whole thing is inundated. Most of the flow is in either diffuse flow or anastomosing channel systems. So you get a sheet of water that's coming down, and most of the water is flowing along the floodplain. But what you see here is an on-echelon system of short water holes. That's the big one called hookies, but there's a whole trail of them. The water flows along the floodplain and goes along, and every now and then it dips down into the channel, and then it pops up again and goes out along the floodplain, and then it finds another different channel segment to dip down into and then come out again. I love this river, it's so cool. So here's the thing. Flow in these main channel segments absolutely relies on floodplain inundation. We tend to think of floods as being first you get the flow in the channel, then the channel overflows, then you get floodplain inundation. No, it's the other way around. You need to have floodplain flow for the channels to be properly activated. Obviously, this is a little bit dependent on place, but that's basically the picture. The last type of channel that I want to talk about in highly variable rivers is a place that has no channel at all, and that's the floodout. A floodout is a really cool thing. They are all over Australia, but I've had overseas geologists and sedimentologists tell me that they don't believe it exists, but they are all over the place here. So what happens with a floodout is that you get a river reach that is kind of semi-constrained within its valley. For some reason, it's got hills or terraces on either side, and then it comes out and it enters into the plain, and the flow becomes unconstrained. So the river gets the chance to spread out, it gets wider, therefore it gets shallower, therefore the energy level drops, therefore it drops all its sediment, and all the water starts to sink into the dirt, and the channel disappears. So you have river channel, no river channel. And the flow continues overland as sheet flow, completely unconstrained flow. This is functionally equivalent to the riparian zone in a creek, except it's not on banks because there's no channel here. But you can see here in Aridity floodout in South Australia, again, all that black is vegetation. You can see that this floodout is supporting a really big terrestrial ecosystem here. And you can get these floodouts on small creeks or big creeks. This is the Amungana floodout on the Todd River in the NT. So the Todd comes down from the Mac Ranges and it floods out here near Amungana, and then the channel reforms and it continues on to the desert, to the Simpson Desert, sorry. So these are very important for ecosystems, but they are very, very vulnerable to erosion. So they need management, but they're not even recognised in how we talk about rivers. They're certainly not afforded the kind of protection that funding for rivers attracts, or legislative protection for rivers. So the next application here is something that I'd really love to see happen. Can we kind of broaden fluvial concepts to include things that happen in dry lands and highly variable rivers? It means thinking differently about flood height or width, as the case may be. We defined flow regimes as the ratio between a certain kind of flood and base flow, but we can't do that if we don't have base flow. So how do we even calculate flow regime? Bankful is a thing that has less meaning than people might think, and other things like stream water and what qualifies as riparian vegetation. So I'd really love it if we could bring this terminology along and apply it in a way that's meaningful to the rivers in the Australian drylands. So in conclusion, I think it's fair to say that sustainable land and catchment management has absolutely got to rest on a true understanding of landscape processes. If we're just making stuff up, we're not in a good position to make good decisions about managing the landscape. Inland Australian landscapes deserve the same care that we give to other places. So if we're having to work with our stakeholders to decide what's valuable in our catchment or our locality, and we need to create strategic adaptive plans for our landscape, we need to be able to name and understand dryland's fluvial characteristics. Finally, in a future where extreme climate events are likely to occur, I think we're likely to get more highly variable rivers, and I think it would be good if we could act with a greater understanding of those conditions. Thank you so much for coming out tonight. I'm open to questions.
I think I'm up to bank full on terminology tonight. That's the best fluvial geomorphology lecture I've ever had. Really good. I really enjoyed that. I've had twice, forget the carbon footprint, I've twice flown from Dubai into Europe this year across those magnificent landscapes that you had a big X on through Iran and Turkey, and it's quite extraordinary. It's the reason why you always have to have a window seat, especially on those flights. I'm also, I've learned something. I'm doing some work with a company, the Australian Rail Track Corporation. Apart from the road culverts on roads, this problem that you've talked about tonight on railway lines is massive. So it's all very well driving along in a car at 60 or 100 Ks, but if you're on the front end of a train and all of a sudden the tracks aren't there, it's a big problem. So we might talk about that later, because I might need you to come and do some consulting. Anyway, because yes, I'm sure that was really interesting. My only question, because I think the audience have a question, what does boom bust mean in a time of climate change? Because I figure that these things that you're talking about are probably changing. I mean, the Fitzroy flood, Fitzroy Crossing flood, Are we seeing more of that and more impacts? Is the dynamism of these systems changing noticeably in your lifetime?
That's a really hard question to answer, partly because we don't, would it be easier if I did that in the mic? No, you're going to do that, okay. Partly because we don't effectively monitor how much flows we have, and we don't have a very long flow record history. So we don't actually have a terribly good picture in most places what even constitutes a 100-year flood. So I'm not a hydrologist, I'm purely a geomorphologist. So I couldn't answer that question, but I suspect that we don't even have the information to answer that question.
Let's get some questions. There's a roving mic, and just let us know who you are. There'll be some online as well. Right at the very back, first of all.
Yeah, look, a terrific presentation, just engrossing. Thank you so much. If we think about things like, say, management legislation, statutory protection, we had, say, the Commonwealth Environment Protection and Biodiversity Protection Act. Have we got sort of triggers, or could we come up with science to say these are triggers which could trigger protection under that sort of Commonwealth legislation, or are we just at the stage where we just don't have that trigger, so we can't think of triggering, say, a Commonwealth Environment Protection, Biodiversity Conservation protection?
A very large question. The legislation that looks after biodiversity is, I mean, I don't know much about it. Obviously, live things aren't really my jam, but it's all about, you know, things that you can measure in terms of species. The legislation that looks after rivers and waterways has different kinds of definitions and triggers, and the laws are different in different states. But one of the things about triggers for management actions is that the landholder stakeholder groups, the catchment management groups, these are the ones who are actually thinking about and putting these things in place. So, you know, what I'd ideally love to see is ways that we could support with science the people, the landholders who are making the decisions out there on country.
That makes a lot of sense for CMA trying to deal with legislation on biology in the EPBC Act, and rivers simply don't talk to each other. That must work really well. Another question. Oh, yeah, online? Yeah.
Yes, we've got one from YouTube. So Van Pelt, hello. The question is, and it relates to the previous question, it gets to mandates and it gets to regulation, which is unsure if you'll see this live. We've seen you, but mentioned culverts being typically undersized and causing issues. Do governments need to mandate planning for larger events, obviously increasing costs?
So governments don't need to mandate for larger events. We could be doing much better with the events we're already having. Okay, so that's point number one. We need to actually be responding to the conditions we're experiencing now before we even think about what's happening in the future. But you know what? It's not about governments mandating. It's about governments resourcing science in the rural and regional areas. So the people who have to make decisions about how to design roads and flood zones and stuff don't have the scientific support. I mean, I've been working in the public sector one way or another since the mid-70s, and the withdrawal of scientific advice that's available to people who make decisions, I think, is one of the greatest shame jobs of the country, frankly.
Thank you, Doctor, for a spectacularly good presentation. I'm very grateful to you. My name is Paul Kouris. I'm a barrister by profession and an inventor by vocation. And a lifetime ago, I dipped my toe, no pun intended, into fluvial geomorphology. And I remember being taught that the Coriolis force had an impact on the meandering of rivers. And I was wondering whether there was any studies that have been done recently through climate change to explain whether the meandering of rivers have been affected by climate change, and if that is an issue that also has an impact on the dry river systems that you're talking about?
That's a really interesting question. I had not particularly considered that. Because dryland rivers are so highly variable anyway, and because they are so understudied, I think it would be very hard to say. It would be very hard to say how much change that is happening in the landscape is event by event, determined by some aspects of climate change. Yeah, that's a really hard one. But I think the things that are more likely to affect the ways rivers meander is not the Coriolis force. It's that the volume of water that you get in the river is going to be really strongly impacted by the longer dry spells, or alternatively, the more intense atmospheric river wet periods. And so that is more likely to do things like, many of you will know, the scale of the meandering scales to the size of the water flow. If you have larger flow events because of extreme weather events, I would think it likely that you would get an increase in the rate of meander development, and that would lead to a more rapid bank erosion and more rapid channel migration. And many people who live by rivers already have difficulty with the idea that channels migrate, and so that would probably be a problem. I have to say I don't do a lot of work in meandering rivers, so it's not really my area.
So more braided streams and less anastomosing streams.
Oh, them's fighting words. I think it's unlikely that any of our rivers would start to braid, no matter how big the energy.
Question.
Thanks for your talk. There's a group of politicians who want to dam every single river in Australia, including the Channel Country. Can you outline the effect of even one or two dams, what effect that would have downstream? Colorado.
Okay, so yeah, you saw the hydrograph of the Colorado. It depends what people want to do with the dams. And there's a scale of dam from tiny little farm dams to great big, go across the entire flow path. If you cut off a flow path, let's say one of these floodplain level flow paths, if you cut off a flow path, you will be depriving the downstream ecosystem of the water it needs. Now, it then becomes a management decision whether or not you're going to have a sacrifice zone. The food we eat all comes from sacrifice zones, right? Whether we're eating vegetables or animal things, there's some place where we've chopped up the ecosystem and put it to service for food production. And as long as we're honest with ourselves that that's what we're doing, then, you know, good. But what you can't do is throw a dam across a highly variable river and pretend that that's okay for the ecosystem, because it's not going to be.
Letter to the editor, Bill. Are there other questions? Another question. Yep. Two.
John, it would have broken my heart if you hadn't asked me a question.
Roads have to cross these dry riverbeds, and you're saying that the culverts are a bit small and don't work too well. What's your preferred engineering solution?
Really much bigger culverts. It's as simple as that. There's for the smaller creek crossings, either just put up with not having a raised crossing, like, you know, for the smaller places, you can't put a culvert on everything. Just have a road that gets boggy with sand occasionally. That's kind of rural life. For the road crossings that need culverts, have bigger ones and calculate the flow volume as if it's got to encompass everything that fills up with that valley. That's the key step that isn't happening. And with big bridges, like the bridge across the Fink or the Napa Bridge just on the Queensland border, there's a thing called bridge abutments. So people put in bridges and they narrow off the valley, and it increases the flow that goes through under the bridge, and surprise, causes a bunch of bank erosion.
Yeah.
So, you know, I think basically we need to just not look at the channel and say that's where the water is. We need to look at the entire valley and say all of that is where the water is.
Hi, Grizzly. Yeah, thanks for a great talk. More of a geological question. So if in these valleys that we're looking at, we talk about the surface water flow. In the times when you don't have surface water flow, is there underground flow in the same area following the same channels, which is presumably keeping the vegetation going? And is that measured? Can you measure it?
I am not a groundwater person, but I know somebody who is, and I hope she's watching tonight. The answer to that question depends very much on the local geology. So the Fink, for example, which is a sandbed river and has sandy floodplain and sandy banks, it absorbs quite a lot of the water that flows in it and feeds it back into the terrestrial ecosystems over time, because basically its floodplains are porous and permeable. Other places like the Neils, the one with the little discontinuous channels, that is essentially a valley that's cutting down into not very permeable Eromanga Basin rocks. And I don't think that stuff stores very much groundwater at all. So it very much depends on the sedimentology of the alluvium and the underlying geology of the area.
Mike Williams, the problem of drainage generally and across the Australian continent, there are many areas in what you would call wetland. But the point here is that every time you go along a road in Australia, not every time, but mostly you're driving on top of an embankment. So we have in our areas of living, you have a similar problem in that surface drainage has been obliterated by roads. And what happens there is that the river does dig down, but not only makes a bigger hole, but it also will lower the level of the groundwater. So there are relations, similar problems of surface drainage which have been interfered with consequent damage to the, if you like, watering of the land around.
Absolutely. And you know, ideally, fluvial geomorphologists would be involved in every step of the planning of all sorts of road and engineering works, and that railway, of which we will not speak, that goes across all these low-angled alluvial fans. Yeah, it's a problem in so many places. And I think, I mean, the consequences are not only damage to the landscape, there's some particular kinds of damage to the rural populations as well. So one of the things, as a person who's volunteered for years in environmental organisations, is there's this whole big discussion about the role of overstocking of sheep or cattle or whatever in creating landscape damage. And, you know, no shade on that, that was absolutely a thing. But there are so many places now where people touristing from the city come out and they say, oh, there's a gigantic galloping gully network. The landholder has overstocked here, and it's not. It's the way we build our roads. And you can destock as much as you like, and it's not going to address the problem. So yeah, we need more fluvial geomorphologists everywhere.
So more money for science, more data, so we can actually get better results. It's pretty simple.
I mean, you know, we could be a smart country.
Right at the back.
Being one of the unfortunate public servants who's got to deal with condition frameworks for monitoring, is there anything you can suggest for the dryland rivers, particular earth observation being kind of the driving force now in government departments?
how much budget are we fantasizing here? Are we talking?
Limitless for fun.
It's cabinet in confidence, I'm afraid. So
Fair enough. Okay, so let's say within the constraints that exist in the present day, probably the key point is just to recognise and maybe document or acknowledge the sampling bias that takes place. So this thing where we only look at the rivers that have got wet bits in them, you know, the first step is to say we are ignoring whole other swathes of the countryside. After that, with a very limited budget increase, I would think that it would be possible to update some of the standard schemes with, for example, biota lists that don't include fish and yabbies. So get a herpetologist on board and talk about reptiles, snakes, termites and ants, for example, would be a fabulous way to measure the health of floodouts.
Let's take one more question from online. Mike has one.
Yep, thank you. This is Tom Brooks on Zoom. Tom asks, in your opinion, what is the characteristic sediment deposition of a dryland river environment, or is it highly variable?
It is highly variable. So it depends very much on the geology and the regolith in the contributing hill slopes. And also it depends a little bit on the sediment transport capacity of the river. If we look in the Lake Eyre Basin, as an example, the rivers that come out of the country that's got like beautiful ranges, the Flinders, the Western Macs, those rivers carry a very high load of quartz sand, and so their sedimentary pattern is lots of nice porous sands, which is nice. The rivers that come out of anything that drains off the Eromanga Basin or the Great Artesian Basin, so that's all that black soil country in Western Queensland, that drains mud aggregate fragments. I don't know, anybody here ever got bogged in that country? Yeah, okay, so it's kind of wet and squishy, but biologically enormously productive, like it's really important agricultural land.
Okay. Now,
Sorry, I just
Sorry, Mike.
just went kaboom there. Sorry about that. There's just one more question
Yeah,
on
go.
Zoom, if I may. That's from Francine Noble. And she's interested to this is good for a Victorian society, Rob, interested to understand Victorian examples of dryland river systems. For example, in the Wimmera, maybe Yarrambiack Creek or Wimmera River, that sort of thing.
Okay, so Victoria's interesting in this respect that we have rivers that are kind of nearly dryland rivers, like the Yarrambiack, yep, the thing you just said, and the Charlton and things like that. I don't tend to think of them as being particularly drylands rivers. They're on more of these beautiful low-angled fluvial fans, and they're coming down from the highlands, and they're often quite wet. They are a little bit highly variable, but I haven't done a lot of work in Victoria. The driest parts of Victoria are up there in the northwest, and they're quite sandy and they don't have surface drainage to speak of at all. They've got other interesting geomorphology, but Victoria is a less prolific place for drylands rivers.
Great. I'm going to assume, Grizzly, that your comments about roads and railways in dry rivers have been taken straight to the point that we need. The gentleman at the back is going to take that exactly to the place that needs to be discussed. We're going to assume that. That's been a fascinating discussion, and I'm sure the audience here and online has thoroughly enjoyed it. I'm now going to call on Dr. Anne-Marie Tossolini, who is the chair of the Victorian Division of the Geological Society of Victoria, to pass a vote of thanks. Welcome, Anne-Marie.
Thank you, Rob. Grizzly, it was an amazing talk, and you've really shed light on how extensive the drylands and the dead heart of Australia really is. And so it's extraordinary to think that there's such little still known about that. But you've really given us amazing insights tonight and fantastic pictures. So I'd like you all to join me in thanking Dr. Grizzly Wakeling-King for her fantastic talk this evening. Thank you.
It's been a pleasure. Thank you very much for having me.
Thank you, Gresley. Now, can I invite all of you to join us downstairs for some refreshments and further discussion. Thanks for being with us, and thanks to the people online.